being live streamed up at the top. So okay.
And you can go to presenter mode or something, can't you, Erica? Oh yeah, good. Just making sure.
Yeah, yeah. I probably should have started that way anyway, because I don't know. Were you here when I was talking about my tabs that are open? I think
No.
you entered after that. But
Okay, I'm going to go ahead and start a recording of it onto my computer just in case something weird happens. And we should be ready to go. So go ahead. Everybody else, if you could mute, we'd appreciate it. And I'm trying to remember how this all worked. It's been a while since we've done a fully virtual one. So let's do it.
All right. So welcome everyone. Today we're at the Master's Defense for Erica Bortfeldt. Erica was born and raised in Colorado, where she attended the University of Colorado Boulder and got her undergraduate degree in atmospheric and oceanic sciences. While there, she worked as a learning assistant for applied mathematics, as well as a teaching assistant for an introductory meteorology course. And she spent time her senior year doing an independent study with Dr. Andrew Winters on tropical cyclones undergoing extratropical transition. And then Erica came to join us here, UW-Madison. She started in the professional master's program and worked with Coda Phillips and myself doing some research. And then at the end of that first year, we decided that the research master's program might be a better fit for her. So she transitioned to that program, and we have been working on this work that she's going to present today ever since. And with that, I will hand it over.
all right. Thank you, Mike. So today we're gonna be looking a little bit at the performance of PATMOS-x in global and regional analyses of clouds and as they relate to Earth's record low planetary albedo in 2023. So in 2023, the CERES-EBAF dataset, which is a well-vetted and widely used radiative flux focused record composed of data primarily sourced from the Aqua and Terra satellite platforms, showed a record low planetary albedo, as well as a general steady decline in global mean planetary albedo throughout its entire record. So, in the specific context of the strong 2023 negative albedo anomaly, clouds are considered the primary offender. This is because clouds as a whole are highly reflective, cover about 50 to 60% of the planet at any given time, and they can be extremely variable on a short-term scale, meaning an anomaly related to clouds is likely to be revealed in something like albedo at the same time that that anomaly occurs. There's unlikely to be any significant lag between a relevant cloud-based anomaly and the reflective efficiency of the planet. Now, this is all well and good, except for the fact that the CERES-EBAF dataset falls pretty short where cloud analyses are concerned. This is due to a limited optical depth range, which can't capture the thinnest or the thickest clouds, and the fact that it supplies a cloud effective pressure variable rather than a cloud top pressure variable. And for reference, effective pressure measures at the point a cloud is deemed most reflective. But this has the same effect as the limited optical depth range, except the problem is now that we can't capture the highest level clouds or the lowest level clouds. So this makes in-depth cloud type specific analyses virtually impossible, which means we need a separate data set to analyze the role of clouds in 2023's planetary albedo anomaly. So that's where PATMOS-x comes in. PATMOS-x is a global satellite record containing data from 1980 to present day with an explicit focus on cloud properties. It includes the full ranges of variables necessary for individual cloud binning and typing, particularly optical depth and cloud top pressure. And while we can't easily reproduce planetary albedo from it, its channel 1 visible reflectance variable is a suitable analog for albedo. because it's sensitive to bright targets, making it a pretty reasonable measure of reflected solar radiation. Also, because it extends all the way back to 1980, we ideally have the capability to see if apparent trends that we see after 2000 start and continue before it. So there's a catch, though. PATMOS-X is an AVHRR-based record comprising 16 different polar orbiters, none of which were intended for the purpose of long-term climate monitoring, nor do they feature onboard calibration. Each of those satellite platforms has a different set of local overpass times and differing degrees and severity of orbital drift. So as can be seen by this global monthly mean cloud reflectance time series, all of these challenges kind of come together to produce what essentially amounts to an unintelligible disaster in which nothing climatologically relevant can be gleaned. But that doesn't make the record useless. All it means is that we need to validate the most recent vicariously derived intercalibration, which is the process of correcting for time-dependent sensor degradation with the added goal of bringing all of the different satellites' measurements into agreement with each other. And we need to perform some level of solar zenith angle-based normalization on the channel 1 data to handle the impacts of orbital drift and local overpass time discrepancies between satellites. So ultimately, our overarching goal is to determine if PATMOS-X is a viable dataset for investigating global cloud effective reflectance. And along the way, we also want to determine if the record's intercalibration adequately resolves the effects of sensor degradation, if the solar zenith angle normalization methodology that we follow does a good job of removing uncertainties due to orbital drift and local overpass time differences, and even further, if this normalization holds up when the scope of analysis is broadened beyond the calibration validation phase. And then finally, we want to figure out if PATMOS-X effective reflectance agrees well with the CERES-EBAF planetary albedo. So now that all of that's been established, we can finally move into the calibration validation and normalization portion of this analysis. So for this phase, as well as the whole project, the PATMOS-X level 2BC record is used. It's sampled at a 1 degree by 1 degree spatial resolution, which makes it 100th the size of its level 2B predecessor. So this ultimately means it's much more easily processable. And for the purposes of quantifying long-term climate trends and anomalies, this easier processability does come at, or does not come at any significant expense of data accuracy. So our calibration validation procedure relies on the principles of stable target methodology, which essentially compares climatologically stable Earth target reflectances from AVHRR, typically those retrieved over bright deserts or ice sheets, things that we know do not change in reflective character over time. And we compare those against those measured by well-calibrated sensors like MODIS. The AVHR reflectances are then adjusted according to the comparison results through a derivation of a calibration slope, which contains 3 coefficients. Now, I do want to clarify, this stable target methodology is being described in the context specifically of our calibration validation procedure. In actuality, while the PATMOS-X intercalibration does have some stable target-based calibration techniques kind of wrapped up in it, it's derived primarily from simultaneous nadir overpass comparisons between AVHRR sensors and with MODIS. And SNOs describe scenes where the satellites of interest are all viewing the same location at nearly the same time for the purpose of more direct comparisons between measurements. So the reason introducing a stable target-based validation for PATMOS-X is considered novel is because the intercalibration is mostly not derived from stable targets in the first place. So we're introducing a separate method on the assumption that the intercalibration was already shown to be effective from the SNO comparisons. So we want to see if that effectiveness holds up using stable targets as well. So that said, let's talk about deep convective clouds. So deep convective clouds are a slightly more unique target for this method. but they serve their function pretty well because they're high up in the atmosphere, meaning they're visualized very easily. They're extremely bright, and they generally have a narrow reflectance range, which limits uncertainties in comparison or calibration assessments. Um, so, for our purposes, we'll use DCCs to evaluate the 2023 set of PATMOS-X calibration coefficients. And if by the end of the validation exercise, the monthly mean time series of deep convective cloud reflectance is kind of flat and stable, with a maximum uncertainty of about 4%, the calibration will be deemed sufficient. And 4% may seem like an arbitrary threshold, but that number kind of comes from the limitations of AVHRR as a somewhat outdated sensor. The MODIS sensor uncertainty threshold, for it to be considered a well-calibrated sensor, is around 2 to 3%. And that's because it's a more modern piece of technology. It's more sophisticated, as is demonstrated by the fact that it even has the ability to continually recalibrate itself to begin with. So given that AVHRR was never even designed with climate monitoring in mind, a 4% uncertainty maximum is considered actually quite good for the circumstances. So we begin by filtering the level 2BC data for DCCs. And since DCCs are exceptionally cold, we first set the brightness temperature to less than 200 Kelvin. We then want to limit solar zenith angle to less than 80 degrees. So we're not really capturing excessively dark scenes. And then we wanted to restrict the sensor zenith angle, or the viewing angle essentially, to less than 15 degrees. And that's pretty strict. That's near nadir. This is to try and limit 3D shadowing effects. Those effects are still present, but they're not nearly as disruptive at near nadir angles as they are at more oblique viewing angles, where the sensor can't really capture the highest intensity reflectance. And then finally, we will grab samples only from the tropics, since DCCs there are physically consistent. They tend to be taller, more optically thick, and therefore brighter. So next, we'll perform a count to reflectance conversion. AVHRR doesn't actually record reflectance. It records what we refer to as counts. And those are pre-calibrated unitless integers that are related to reflectance. But an important thing to note here is that the AVHRR-3, which flies on all the satellites in this record post NOAA 14, is a dual gain radiometer. So this means it has two different modes, one for viewing dark scenes and one for bright scenes. And ordinarily, this would also mean the conversion equation that we use would have to be applied differently to high gain or bright scenes, as opposed to low gain or dark scenes. But the equation has been modified to kind of treat all satellites as single gain platforms. So that equation will take the calibration coefficients of each of the satellites in the record as inputs in order to convert the unitless DCC counts to calibrated reflectance. So first we have to calculate the gain, where S1, S2, and S3 are the coefficients for a satellite's calibration slope. And delta T kind of denotes the amount of time that has elapsed since the launch date of that satellite. A rudimentary reflectance value is calculated by multiplying the gain by its associated count. And then the Sun-Earth distance is computed, where the lowercase d here represents the day of the year. And this serves as an important adjustment factor that accounts for reflectance being, on average, brighter or dimmer, depending on the time of year, due to Earth's elliptical orbit around the sun. Then we retrieve our final reflectance value by multiplying that initial rudimentary reflectance by the Sun-Earth distance factor squared. And then, when this is all put together, we get a time series of tropical DCC reflectance that is completely uncorrected for orbital drift and local overpass differences, which still looks like a hot mess. But we expected that. No normalization has even been applied yet. So now, we devise a strategy to handle that problem. In level 2BC, the provided channel 1 reflectance variable already contains a solar zenith angle normalization, which divides the uncorrected reflectance by the cosine of the solar zenith angle. However, as can be seen here, it clearly doesn't do a good job at all of handling drift. And this is because it operates on a Lambertian assumption, which treats all targets that a satellite sees as isotropic reflectors. But this very much breaks down in a real world context because most surfaces are at least some level of anisotropic. They don't reflect radiation equally in all directions. So we have to derive our own corrective relationship. If our uncorrected DCC reflectance is plotted against solar zenith angle, we can obtain a simple second-degree polynomial expression to define how our target's reflectance responds to solar zenith angle. If we then apply that relationship to the uncorrected reflectance by computing a reference reflectance at solar zenith angle of 20 degrees, and then we obtain the reflectance at every solar zenith angle according to the fit line curve. And then we calculate the degree to which that reflectance deviates from the reference reflectance at 20 degrees. And finally, that we add that offset back to the associated uncorrected reflectance value. We return a time series that looks like this, which looks miles better than where this whole thing started. So taking it a step further, if we want to add a safety net and double check both the calibration itself and the efficacy of our normalization, we can apply all the same DCC filtering criteria and normalization methodology to the ISCCP-NG Level 1G demo dataset, which compiles data from all geostationary imagers from 2021 and 2022. And all satellites in this dataset feature onboard calibration and are considered consistently well calibrated, which makes it an ideal candidate for comparison. And this is what that comparison looks like, demonstrating an overall remarkable agreement between a known well-calibrated reference dataset and PATMOS-x. The reason that this further validates our calibration validation obviously lies in this agreement. If the relationships are in agreement with one another, that implies the effects of time-dependent sensor degradation in PATMOS-x are reasonably well resolved by the 2023 calibration. And the remaining data inaccuracies, for all intents and purposes, are related to purely to solar zenith angle dependent phenomena, which orbital drift and local overpass differences are. So, taking one final step to compute a monthly mean of corrected DCC reflectance across satellites yields a much more readable result than we had at the start. And if that lower plot is zoomed in, we can see that if the, or with the exception of like some sparse outliers, the mean DCC points are largely confined within a 4% range, meaning we can, with reasonable confidence, kind of declare that the PATMOS-x intercalibration is valid. With that established, we can now finally move on to a broader analysis in cloud effective reflectance, which I'll explain here in a second. But first, because we kind of did that whole validation exercise and you might feel like, where is this going? Here's a reminder that our big goal here is to determine if PATMOS-x is, in an analogous manner, capable of visualizing this albedo trend and this anomaly that CERES reveals from a cloud perspective. We want to determine on a global and all cloud type scale how clouds may have contributed to that 2023 albedo anomaly. But the explicit role of clouds in albedo can't be quantified by their total reflectance alone. Some clouds are more common and widespread in the climate system than others, but some clouds that are less common are altogether more effective reflectors than those that are more common. Than those that are more common. So we have to compute a new reflectance-based quantity that accounts for the cloud fraction, and we call this quantity cloud effective reflectance. The mean of which we can define both spatially and temporally, depending on whether we're looking at time series or maps. In either case, we're returning a quantity that is the result of dividing the reflectance sum by the number of cloudy pixels plus the number of clear sky pixels. The denominator is the part of this equation that kind of encapsulates the added effect of cloud fraction. But we don't just want to visualize the role of all clouds put together, though. We want to get a deeper look at different cloud types and cloud bins. So here we follow the ISCCP cloud type map, which is based on thresholds of cloud optical depth and cloud top pressure to perform specific cloud typing. But instead of calling the clouds by their names, we'll go ahead and generalize the definitions a bit and name them simply by their level bin and their optical depth bin. So the optical depth bin names come directly from the relationship between the thickness of a cloud and its reflective capability. Thinner clouds are much less effective reflectors than thicker clouds. Therefore, they are dark clouds compared to bright clouds. This naming convention is more explicitly descriptive of each type's characteristics, and it makes it easier to understand which ones are dominant contributors in reflective anomalies. We'll then kind of draw on the same solar zenith angle normalization methodology from the calibration validation exercise in phase 1 and derive a reflectance solar zenith angle relationship for each of the 3 optical depth bins. And ideally, this would bring all the satellites at all latitudes for all cloud types across the entire record into agreement. Unfortunately, it winds up not being so simple. Individual cloud typing on a global scale immediately complicates the analysis, and more specifically, the solar zenith angle normalization that we're able to apply. In particular, dark clouds have a tendency to record unphysically bright reflectances often enough to introduce significant error and overcorrection upon application of normalization. For instance, the high error points, which we define as greater than 20% here, off the mean reflectance solar zenith angle curve, that we can see in these figures of low-level dark clouds that those high error points are largely condensed near the poles, which suggests the primary issue is that the dark clouds are so thin that the bright ice sheets underneath them dominate what the satellite sees reflectance-wise. This is probably this is generally a fault of one key assumption that we're making when sorting clouds by optical depth. We're essentially assuming that all clouds across all optical depths are functionally opaque, and that's just not true in a real-world context. A satellite may be able to proficiently detect that a cloud is there, but if the cloud is particularly thin, it can be translucent enough to show the surface below it. And there's a significant probability at that point that if the surface is bright, as in the case of ice sheets and snow, the sensor will record the reflectance of the surface instead of the cloud. Now, you would think, given that all the higher points that we're seeing on this map are distributed at high latitudes, particularly in the poles, that all we'd really need to do here is add an additional filter to omit reflectance samples where clouds are detected over snow and ice. That way, we'd still be able to maintain a global analysis mode. But while the same high error points or pattern arises with mid-level dark clouds, that can't be said for high-level dark clouds, which show a large concentration of high error points all over the place and mostly over deserts and just kind of large swaths of landmass. So we're essentially forced to apply a landmask and view clouds over oceans only. We don't want any cloud samples over land masses, so we can avoid incorporating high error reflectances in the analysis. But this means we already no longer have the ability to perform a complete global analysis, which similarly degrades our ability to compare the results against what we're seeing with CERES. We can still evaluate the performance of PATMOS-x in a broader context, something beyond the narrow scope of the analysis that we featured in the calibration validation. With that said, We first obtained the landmassed solar zenith angle relationships for each of the optical depth-based cloud bands. And notice for the dark cloud bin, there's no longer a branch of unphysically bright reflectances, so that's great. And the dim cloud bin has a wider spread of reflectances at lower solar zenith angles, but that's somewhat to be expected considering it's the bin featuring kind of like the broadest range of optical depths. So when we put it all together, we compute the cloud effective reflectance, we apply the appropriate solar zenith angle relationships, and we deseasonalize the record to remove all of the excessive seasonality signal that becomes highly prevalent in more global analyses. We obtain our first 1980 to 2023 monthly mean anomaly time series, looking at clouds over the oceans. And for the most part, the best agreement between satellites is shown with dark clouds, interestingly enough. There are some discontinuities here and there with the early satellites, which could easily be a feature of there being fewer satellites flying at any given time, as well as their tendency to drift more than later satellites. Some satellites also consistently record lower reflectance or lower effective reflectances than others. But I guess if you kind of draw your attention to the y-axis range, which only spans about 1%, these discontinuities and small disagreements are somewhat insignificant. It's not until we move down to the dim and bright clouds here that we start to see a breakdown of our normalization method's effectiveness. So in these figures, we see drift signals still appearing in pre-2000 satellites that are greater than 2% in both cases. And even a bit of those drift signals bleed into post-2000 satellites as well. These signals only become more prevalent when we switch to a level-based perspective, where high-level clouds demonstrate kind of extreme discontinuities, particularly between NOAA 12 and NOAA 14, and some pretty stark disagreement after 2020, where NOAA 18, for whatever reason, branches pretty far away from the rest of the later satellites. Mid-level clouds also show drift issues and discontinuity, particularly between NOAA 14 and NOAA 16. As well, like low-level clouds demonstrate this same discontinuity, as well as consistently lower reflectances from NOAA 16, 18, and 19, as opposed to NOAA 17 and the MEDOPS. So when we put all of these cloud types together to look at the combined effect of all clouds on effective reflectance over time, we again see strong drift signals appearing pre-2000 and a sharp discontinuity between NOAA 14 and NOAA 16. And you're going to see a pattern arise with NOAA 14. It's a real infuriating satellite. But this ultimately means that we can't perform a fully direct comparison against Ceres planetary albedo. I mean, we can anecdotally say that post-2000 cloud effective reflectance over the oceans from PATMOS-x does seem to follow the same general albedo downtrend observed by Ceres. But based on the fact that we observe peaks and dips in the PATMOS-x ocean cloud effective reflectance, we observe those kind of at the same place that we observe them in the Ceres planetary albedo. And you can sort of say that it looks to some extent that in 2023, clouds over the ocean did contribute at least partially to the negative albedo anomaly. But we've identified too many sources of uncertainty to confidently quantify to what extent those clouds actually contributed to the albedo anomaly. There's also the added challenge of the Ceres albedo curve factoring landmass reflectance into its calculation. And, since land masses and ocean surfaces are much less likely to be significantly variable on a month-to-month basis or a year-to-year basis, they reliably tend to offset anomaly signals from clouds on a global basis, unless those signals are especially prominent. So overall, attempting to draw explicit conclusions on a comparison between Ceres global, like all-sky albedo, and PATMOS-x cloud effective reflectance only over the oceans isn't really a terribly worthwhile endeavor. But what we can do is perform regional comparisons over an ocean. If you've been paying attention every time that this particular albedo map has shown up so far, I'm sure this strong negative anomaly signal over the central Indian Ocean hasn't escaped your notice, because it didn't escape mine either. In fact, I became so invested in it that I decided to look deeper into the radiative flux anomalies there. And that same signal shows up in absorbed solar radiation, where there's a strong positive anomaly. Top of atmosphere long wave flux anomaly, where it shows there's significantly more outgoing long wave radiation in that region in 2023. And even the PATMOS-X ocean cloud effective reflectance anomaly. So this all suggests to me that whatever's going on there, albedo-wise, like in this region in 2023, has everything to do with clouds, and that kind of makes sense. So to confirm this, we'll perform a case study of the Central Indian Ocean. So here we have the cloud effective reflectance for all cloud types from 1980 to 2023 over the Central Indian Ocean. And while we do see some of the same disagreements between early satellites and NOAA 14's inevitable discontinuity nonsense, there's remarkable improvement in the later satellites' agreement with each other, and no extreme or particularly discernible drift signal. If we break it back down into cloud optical depth bins, we can observe a relatively stable slight downtrend in dark cloud effective reflectance for almost the entirety of the record. NOAA 6 is kind of off on its own, and there's an inevitable discontinuity issue with NOAA 14 again. But overall, especially post 2000, the record demonstrates reasonable agreement. Dim clouds really only show a major issue with NOAA 14's discontinuity, again, and an outlier point in 1995, but otherwise, the record is pretty sound. And then if we look down at the bright clouds, we see that the source of the early satellites disagreements that we saw on the previous slide, showing the effective reflectance of all cloud types combined. But still, post 2000, even with a tiny bit of that issue with some satellites recording consistently lower reflectances than others, the bright cloud record looks pretty solid. If we then look at it from a level perspective, high-level clouds are easily the most stable and reliable to analyze, with all satellites being in agreement with each other throughout the entire record, with the exception of NOAA 6. And this isn't especially surprising when you consider that high clouds are always going to be the cloud types that satellites observe first. So you're just going to have more data to factor in there. And mid-level clouds show disagreement among early satellites as compared to later satellites, but post-2000, the satellites align well with each other. And then finally, low-level clouds also show that same early satellite disagreement that we observed in the bright clouds and the all cloud types analysis, which to me, it suggests that it's specifically low and bright clouds that are the dominant contributors to that early disagreement. So we see that if we narrow the scope of the analysis down to a region like the Indian Ocean, there's pretty stark improvement in how the solar zenith angle normalization that we apply handles drift and local overpass discrepancies across the whole 1980 to 2023 record. Now, we want to compare cloud effective reflectance with what CERES observes over the Indian Ocean, and determine which cloud type specifically could have caused the strong negative albedo anomaly in that region in 2023. And to do that, we limit the analysis to the period between 2000 and 2023. And then we look again at the optical depth bins and the level bins of cloud types. So here with the optical depth bins, even though we observe an apparent downtrend in dark cloud effective reflectance over time and a consistent negative anomaly for the entirety of 2023, we can see in the map to the right that that negative anomaly barely even registers in the Indian Ocean, or really anywhere. And this is to be expected, since optically thin clouds are generally poor reflectors, so even a downtrend in cloud fraction, which again is factored into the effective reflectance calculation, doesn't cause a significant impact on reflectance. Looking at the dim clouds, there's no particular trend over time, but we do see a prominent dip in effective reflectance in 2023. And these clouds as well demonstrate kind of like a negative anomaly throughout the entirety of 2023. In the map to the right, this shows up as a relatively pronounced negative anomaly over the Indian Ocean. And then finally, if we look at the bright clouds, there might even be a slight uptrend in effective reflectance over time. But in 2023, these clouds too demonstrate a negative anomaly for the entire year, just not as prominently. This translates to a faded but noticeable negative anomaly over the Indian Ocean on the map. But it's not really any one optical depth bin of clouds that seems to contribute most to that strong anomaly signal that both CERES and PATMOS-X show. It's actually much more to do with the level. And here we see that the high level clouds definitely take the cake for biggest contributor to the negative effective reflectance anomaly in 2023. In fact, the mid and low level clouds don't even show much of anything in the central Indian Ocean. So if we've determined that it's dim clouds that show the most prominent negative anomaly among the optical depth bin cloud types, and it's the high-level clouds that show the most prominent anomaly among the level bin cloud types, then it's fair to say it's probably high dim clouds that contributed most to the negative effective reflectance anomaly in 2023. And we'd be right to say so. So if we break down the high-level clouds into their respective optical depth bins, we can see, particularly in the maps to the right, that it's the high dim clouds that reveal the largest negative anomaly, high bright clouds. And then when we compare against CERES to validate cloud effective reflectance as a suitable analog for cloud albedo, we can see that especially in 2023, over the central Indian Ocean, PATMOS-X, like all cloud effective reflectance, is in remarkable agreement with CERES albedo. And we can essentially conclude that it's primarily high-level clouds that are the dominating contributor to that strong negative albedo anomaly. And the only time that there's like kind of a relatively significant deviation in PATMOS-X effective reflectance from the pattern that we observe with CERES, it's because low-level clouds exhibited like a slight positive anomaly in that same region. So that all kind of brings us back to the big overarching question, right? Is PATMOS-X a viable data set for investigating global effective cloud reflectance? Well, to answer that, we consider whether the record's calibration adequately resolves the effects of sensor degradation, and if we ditch the standard solar zenith angle normalization and substitute our own, we obtain a figure of stable target reflectance that shows the satellites measuring in agreement with one another and limits mean reflectance within the desired 4% uncertainty threshold. This effectively validates that the inter-calibration for PATMOS-X adequately resolves the effects of time-dependent sensor degradation. And this is further supported by a known well-calibrated dataset, ISCCP-NG, demonstrating a reflectance solar zenith angle relationship for DCCs that agrees well with that of PATMOS-X. But then we ask the question of whether the solar zenith angle normalization methodology we applied in the calibration validation performs just as well in general across all possible analysis scopes. And the answer to that is a pretty resounding no. When we analyze all cloud types over all surfaces in all regions of the world, the normalization method is found to be quite limiting in what it's able to resolve, particularly for optically thin clouds over bright land surfaces. So if we want to broaden the scope of analysis beyond thick, bright clouds in a narrow sliver in the tropics, we've determined that the solar zenith angle normalization is appropriate for PATMOS-X channel 1 reflectance and related products only in specific circumstances. So essentially, it only holds up when the analysis is limited to a regional ocean perspective. And when it's applied to certain cloud types or bins, and pretty much only in the last half of the record. This is further solidified when we run comparisons of PATMOS-X cloud effective reflectance against CERES planetary albedo. The comparison performs really well regionally over an ocean, but the validity of the comparison degrades when the analysis is opened up to a more global perspective on account of all the aforementioned challenges that arise within PATMOS-X. Which brings us to potential future work, right? Since it was the high error reflectance issue with optically thin clouds over bright land surfaces that first led to the analysis getting limited to oceans only, we can maybe revisit the cloud detection algorithm to see if there's any way to help the satellites distinguish between the reflectance of a bright land surface beneath a thin cloud, and the true reflectance of the cloud itself. And the root of that revisitation may begin kind of with reworking the assumption that all clouds are opaque targets. Um, we can also revise how the solar zenith angle normalization is applied, since situating the analysis over oceans only still presented issues with resolving the impact of orbital drift and disagreements between satellites. We can potentially derive a new relationship for each cloud type instead of each cloud bin, or optical depth bin, I should say. And we can also try to normalize to different solar zenith angles, depending on the mean or median solar zenith angle for each cloud type, instead of universally normalizing to 20 degrees across all cloud types. We can also maybe revise how land masking is applied in the context of an oceans-only analysis. I kind of went by it pretty fast, but something that some of you may have picked up on is the fact that the landmask filtering that was applied when we shifted to oceans only doesn't actually do a great job of removing shallow and deep inland water sources, or ephemeral water sources, even though the filter was explicitly written to do so. So this suggests a potential issue with how the landmass components are computed to begin with, and an inadequate filtering of these additional smaller water sources could have definitely contributed to some outlier behavior across the record. As well, we can apply an additional filter to remove samples taken over sea ice. Since sea ice typically isn't filed under what constitutes a landmass, and this too could have been an added source of outlier or anomalous behavior in the analysis. So finally, this also may have struck some of you as a point of interest, but if we return all the way back to the zoomed in, corrected monthly mean reflectance time series for tropical DCCs, there does appear to be the slightest uptrend in DCC brightness over time, which is peculiar considering DCCs are supposed to be characteristically stable in terms of reflectance over time. Whether this is a feature of the sensors used in the record, how the record is calibrated, or if it's a real physical observation is pretty tough to tell, but it would probably be worthwhile to look more deeply into that. So with all that said, is PATMOS-X a viable dataset for investigating global cloud effective reflectance? Well, it comes down to this. In its current form, the PATMOS-X record is not an ideal, consistently reliable dataset for performing global analyses of cloud effective reflectance. However, it is an adequate dataset for use in regional ocean-based analyses. And that's the conclusion. That's it. I think maybe for the sake of time, I'm not gonna do my like thank you speech and acknowledgments, but if you have like a burning desire to know why I'm thanking you specifically, email me. But yeah, I guess I can open the floor to questions if anybody has any.
I'll ask one, just a general one.
Okay.
For people that may not necessarily be into remote sensing, like most of us, the three members of your committee are, when you look at that plot with the anomalies, there are so many interesting features there that may touch upon different areas of this department. Ocean, aerosols,
Mhm.
you name it. Do you want to talk a little bit more about what some of those features are and why is that important within the context of weather and climate change?
Can I ask first to for you to clarify which in particular plot that you're
That right there.
this one? Okay.
Yes.
Well, let's see. Also, can you repeat the question because I totally forgot what you were saying?
So there are a lot of things happening here in terms of the reflectance and where those reflectance anomalies are coming from. That may touch upon different things that we do at this department, not just remote sensing. Like for example, if you look at the tropics where you focused, especially close to the Africa, that anomaly right there, that may be Saharan dust, right? And you have something in the Pacific happening that's very clearly a transition of a major event. So I'm not going to say what, so because I want you to talk a little bit more about that. So what are other features here that may be of relevance for people in this department that may not remember from radiation class what reflectances are? And how is this important?
Well, I'll start with this one because this is definitely the Pacific because that's definitely the easiest thing to touch on. I believe 2023 was I believe that was a pretty strong El Nino year. So that is definitely the Eastern Equatorial Pacific, the what we're seeing there in terms of cloud-based anomaly is potentially an increased activity of deep convection over the ITCZ and probably an additional low cloud negative anomaly because you're being obscured by DCCs. And that's pretty common with El Nino. It just you tend to have a much more active convection going on there. So there is that. That's definitely the easiest one to touch on. I think yeah, the one off of Africa, that was an interesting one that I almost looked into as well to determine necessarily what that was. Um, but like you said, it could definitely be like dust storm signals. And I think uh it's kind of hard to describe, particularly maybe what's going on around the Antarctic here. But like I said, because the land filtering that I applied doesn't account for sea ice, that could definitely be like it's more recording anomalies in sea ice than it is clouds there. Um, you know, so yeah. I don't know if that
No,
full.
that's good. That's perfect. That's good.
Yeah, my question was going to be very much along the same lines. I'm looking at the stratocumulus regions. It looks like off the coast of California, South America, and South Africa, you're seeing three, a very consistent sort of picture of a positive anomaly in stratocumulus as well. So again, I think that Myra's point was there's so much in this graph, and everybody sees different things. Of course, I saw the ITCZ as well, and I guess maybe to follow on with that question, a little bit. I mean, in terms of your future work, do you see focusing on any other, regions? And this is an anomaly for 2023, but I suppose there's also trends in the data set and other years that may have interesting features in other areas. Maybe just to ask a question, if you were to focus on something else in this data set and something that you think you can address with, given all the caveats you just put out there, what would you focus on?
Something that came up a lot when I was working with Mike throughout this whole thing. Um, it's a little bit hard to tell just because of where the central longitude is, but pretty much the entire northern Pacific is in a state of negative anomaly. Um, so I think it would be interesting to kind of see what actually is going on there, and if that was, kind of specific only to 2023 or if there is some particular cloud activity that's happening there the over time in terms of cloud fraction and therefore effective reflectance. Um, we did also mention the off the coast of Northwest Africa. We picked up on a lot of little signals here and there too. Think, but it's like I feel like I'm focusing too much on the negative anomalies. I think there could be some interesting positive anomalies, like you said, with the stratocumulus. Um, I believe aren't those like marine layer type signals? So I think that would also be a little bit interesting to look at to see if again that's a specific to 2023 thing, if it's specific to El Nino even. Um, so yeah.
It is good. It is very exciting. There's a lot of information and potential with what we're seeing here. That's why we're asking those questions.
Yeah.
I guess I have another sort of somewhat technical question, because now that you mentioned the idea that there are both positive and negative anomalies here, I mean, does that give you some confidence in the fact that you've corrected, this particular satellite? It is, adjusted properly. I mean, I think if there was a residual bias in the calibration here, you might expect all of the anomalies to be positive or all to be negative. That would be an alarming thing, right? I think the fact that you have a pretty good cancellation of anomalies in different areas, does that give you some confidence that your DCC correction method has kind of, given some good results as well? Just more of a kind of an anecdotal, I guess, way of thinking about it.
I do think the the conclusion that I draw about especially the solar zenithing normalization that I came up with the DCC validation, where I essentially say that it doesn't work under like all contexts. It's mostly when you're trying to look at like time series and trends over time. I feel like it works pretty well on maps. Um, like I was saying, that it works when you narrow the scope back down to uh, regional analyses, and over the ocean because complex things with land. But especially considering that this effective reflectance anomaly map for clouds pretty well reflects what we were seeing with Ceres, which we know is a well calibrated data set and it's well vetted. So I would say yes, but under certain circumstances. I do have confidence in the normalization if we are kind of looking at maps and if the time series are specifically narrowed down to regional. So yeah.
Actually, I have just a logistical question as well from this map. Is you mentioned how you were one thing you could do in the future is maybe uh, take another look at the masking out of land and shallow water. Is this a mass? You do see a lot of anomalies over land masses, I guess, close to bodies of water.
Mhm.
So is this with the land mask applied, and it's just those are uh, presumably lakes and whatnot that are coming up over the land masses, or is this without the land mask applied?
Yeah, no, this is with the landmask applied. This is, I tried to filter out, like when I was applying the landmask, I defined it as get rid of landmass, get rid of ephemeral water sources, and then get rid of inland water sources. And when it comes to pretty much any of the ephemeral and inland water sources, it didn't effectively remove, um, really any of them. I mean, you can sort of see that like up at the northeast here in North America, that's almost definitely those are like Great Lakes and stuff like that. You could be seeing lakes and even maybe signals from the Nile River in Africa. It's I don't know necessarily if that has anything to do with um the landmask itself and how it operates. I mean, it could even potentially be an error on my part. I mean, the land filter that I applied should work as intended, but I could always revisit that as well. Um, and I mean, and I also I didn't talk about this, but I did try to apply that same landmask with level 2B as well. So I don't think it's even necessarily that it's like a coarse resolution problem, like it's just not capturing the smaller sort of like subgrid um lakes and stuff like that. So yeah, does that answer your question?
Yeah. Yeah.
Well, I guess maybe just to piggyback on that for a second, are there any inland water bodies big enough that you would consider the signals might actually be trustworthy? Or do you think you should really screen out all inland water bodies?
I think potentially something like the Great Lakes might be might be just fine. But, like rivers and small little man-made lakes, I think even like Salt Lake in Salt Lake City is probably not that great. Um I think yeah, I think like Great Lakes and lakes that are like kind of that size are um probably okay, but I hesitate to accept particularly like smaller or sizably smaller um, water sources that are inland just because you could be capturing some issues from land in that way just because of the coarse resolution or coarser resolution of level 2 BC. It might work fine for level 2B, um, but yeah, I don't know. Any other questions? Sorry, gotta plug in my laptop real quick. There we go.
Pete, are there any online questions? I guess if not, I think we can conclude.
There are not. I've been kind of monitoring it and there haven't been any, so good to go.
All right. Sounds good. Well, I guess thank you, Erica, and thank you everybody for joining on this virtual talk. It was an excellent presentation. Everybody have a good rest of your Friday.
All right, well, thank you.
Thanks, Erica. Good job.
Yeah, that was great, Erica.
Mm-hmm.